Swayam Prabha. Digital India. Educated India.
Last class we started with the simple liquid mixtures, and since it was just a beginning, I have to cover it up again. So what we have been talking about last class, I was showing you the slide where I have summarized everything so that you can have a whole picture as to what we are talking about, because we are talking about a mixture a number of times. In between, we are saying it is not an open system, it's a closed system, one component system. So the slide which I showed you, which is the first slide which I had, was a summary of how the flow is for a system when we are talking about mixtures. We have talked about mixtures in gases, where we had talked about the mixing entropy of mixing and Gibbs free energy of mixing. What we have not so far done is with anything with liquids. We do not know. We have established what the uh, Gibbs free energy looks like, and from there we have established what the chemical potential looks like for an ideal gas. We had also gone and seen how the Gibbs free energy, or the which can be converted into chemical potential when we are having a mixing of system, or the delta S mixing of a system. What we have not done so far is the chemical potential of a liquid system. Since we do not know how to go about it, we have to go back and use the equations which we have done for the gases. And in doing that, we will be doing two things: the ideal solution and the ideal dilute solution, and then the mixtures. And the mixture is ideal mixture. And excess function, it is not really part of your syllabus, but I'm going to just mention that what the excess function means and how the diagram looks like. Colligative property, I think I'll take up the next week. So what we are going to do, this was the slide I was talking about. I have made the correction here for the delta G. And the whole thing is, how do we when we have a mixture, that means we are an open system, the fundamental equations get modified, and whenever we are having an open system, we are having a mixing. That means essentially we are talking about the partial molar quantities, the partial molar quantities, and the partial molar G and volume we had taken up in detail. And when we are talking about partial molar quantities, what is the first thing which comes to mind is the Gibbs-Dehaene equation. Gibbs-Dehaene equation, where you have if you have a two-component system, we have so far talked about only binary systems, and here also we are going to talk about simple mixtures. That means we are going to restrict our discussion only on binary system. What we have in addition added, which is also going to be dealing with the partial molar quantities, is the Raoult's law and the Henry's law. We had not done this for the gases. In addition, what we are going to look into, whether the equations which we are going to use for the ideal gases for thermodynamic of mixing, is it going to be valid for the one which we are going to be using for the liquid system. And then we look into the phase diagram and colligative property. So this is the gist of how the open system discussion is going to flow. Or if you have not understood what is the flow, you better see this slide, then you can get the whole picture of when I'm talking about a mixture. That means I'm talking about the open system, and in this open system, what are the things which we have done so far. Okay. Now, for chemical potential of a liquid, we do not know how the Gibbs energy of the liquid is going to change with composition. We need to know that. And for what we have to begin with, we begin with the equilibrium system, because we are all dealing with the equilibrium thermodynamics. And the basic equation in that which we can correlate the liquid and the gaseous system is the equilibria, where the chemical potential of a species is going to be same in the two phases, whether it is the liquid phase or the vapor phase. Okay, so at equilibrium, the chemical potential of a species will be equal in the gas phase and the liquid phase. So this is the basic equation which we are going to use so that we can utilize the uh, equations which we had derived for the gas system. Okay, then we are going to look into the mixtures, how the mixing is going to take place, whether it's going to be the same equations, and if it is, how, if I have to define the G accordingly, we have to see how can we extend that. And what is the consequence of mixing and what causes the deviation from the ideal behavior. In the last class of the gaseous mixtures, I had talked about the deviation in a gas phase, and we had introduced the topic fugacity. Now here I'm going to see first look at to how the non-ideality is established. First I have to know what is the ideal system. Okay, so these expressions which we have here in this slide, these are all derived for a gaseous system. The binary gases, if they are mixed, the G of that gas is equal to the number of moles of that gas into the chemical potential plus the number of moles of the gas B into chemical potential. We have to see whether we can use these things in the liquid system as well. In the gaseous system, we had established that the chemical potential of a substance is the slope of the total G versus the amount. And since it is going to change with composition, so we have that the chemical potential is actually going to change with the composition. Okay, so these are the things we already know. Now we are going to apply these things to a liquid system, and the basic beginning of the lecture is this equilibrium, where we are equating the chemical potential of a species in the liquid phase to that of the vapor phase. So for that what we have to look, for a liquid system, what we are going to look into. First, we are going to look into a solvent and a solute. Both of them are liquids. Okay, so when I talk about a solvent, I have designated all solvents with a subscript in blue. Solvent means they are in excess, and the solute means they are in minor amount. Okay, so what we are going to look into when we are talking about a liquid mixture or ideal solution, we want to define what an ideal solution is. Then the chemical potential of the pure liquid, if I define that, let that be mu A. And since I'm talking about a liquid, that means I'm talking about the solvent, which solvent means the amount which is in excess. So this can be represented whenever I'm talking about a pure system, I superscript it with a star. That is the convention you have for all chemical potential representation for a liquid pure system. Pure liquid system, if you are representing, that means it will be whatever parameter, thermodynamic parameter you are dealing with, it will be marked by a star. So this is the chemical potential of the liquid which is in excess, and that is throughout I have tried to maintain it as a blue sign. So A is blue, that means A is the one which is in excess. Okay, so the chemical potential of the liquid, I usually write L, but in books you do not write L, you just drop the L and use the chemical potential of A. So you have to understand that the chemical potential I'm talking about is the chemical potential of the liquid system. Now, since the liquid is going to vaporize, so the liquid is going to be in equilibrium with the vapor system. So here I can apply the equilibrium equation, that the chemical potential of the liquid should be equal to the chemical potential of the gas of that particular species. And since this is the only one which is present, only liquid is present, only A is present, so I can write down the chemical potential of the liquid A in the pure state is going to be equal to the chemical potential of the A in the vapor state when no other liquid is present. So this is no other liquid is present. So this is the gaseous state which we have. And what does that from the equation of Gibbs energy or chemical potential, what do we, mu is equal to mu naught plus RT ln P, and P is what? This is the vapor pressure here. And always remember, this is a relative pressure, means you have a P naught below always, and which is 1 bar. So this equation is for the gas phase. And the gas phase is in equilibrium with the liquid phase. So I can equate these two equations, and if I equate these two equations, I get by combining the chemical potential of the A species in the pure state is equal to the chemical potential of the A at the standard state plus RT ln P A. And what is PA? This is the vapor pressure of that pure liquid. Because now till now I have not added anything. This is only for the pure liquid I am discussing. So for the pure liquid, the vapor pressure is designated by PA star. Okay. Now I add another liquid which I call as solvent, and throughout the text I have tried to maintain the subscript B for the solute. Okay. And solvent is always marked by a blue A. So if I add something, to the liquid which is pure initially, then I have a different pressure generated. That time I'll be having a partial pressure, right? When now it's a mixture. So if it's a mixture, then we don't talk about pressure, we talk about partial pressures. And what is this partial pressure? It's the partial vapor pressure. So as soon as you add something, the vapor composition changes. So that is why we have to take the partial vapor pressure, and this partial vapor pressure of that particular system after adding another liquid, which is I'm designating as solute because this is in small amount. So this equation becomes the chemical potential of A, that means after mixing the solute B, that is also a liquid, is equal to the chemical potential and the standard state RT ln PA. Now this PA is the partial vapor pressure of the pure solvent, because this is no longer, we cannot use PA star. PA star means only the solvent was there. Now we have another liquid which is used designated as solute. So I have to modify the equation of the chemical potential. The chemical potential modified equation is this equation 2. Please always remember that P naught is below this, which I have not written. Now what I do, now I have to find out the chemical potential after I add the liquid. So how do I do that? I now substitute what is P naught from the pure state. If I know what is the pure state, this is the pure state. So mu naught A is going to be mu naught in the mu star A minus RT. This is what I have written. Now this substitute this mu naught in this equation 2, substitute the value of mu naught A in this. So what you get? You see, you get the mu A, which is the chemical potential of the species A after adding the solute B. Okay. So this is what? This is the chemical potential. From here you are getting the chemical potential of the pure state minus RT ln P star A. That's the pure state which you have got from the substitution. And if you see what is going to happen, you can rewrite this in terms of expression. The chemical potential of the species A is equal to the chemical potential of the species in the pure state plus RT ln PA by PA star. This is the partial pressure of the solvent when the solute is added, partial vapor pressure, and this is the vapor pressure when only liquid was there. Okay. So according to Raoult's law, this PA is equal to this PA, which is, what is this PA? This is the partial vapor pressure of the component A when the solute B is added. That is equal to the mole fraction of A into the vapor pressure of the pure state when the liquid was not added. This is the Raoult's law. Now, if you substitute the Raoult's law, then you get the expression of something like this, right? PA star will get cancelled. So you are left with only the mole fraction. So you have the mole fraction here and RTLN, the mole fraction. This will be always a negative term. So you can understand the chemical potential of the species A after addition of the solute B will become a mixture, then that will be always less than the chemical potential of the pure phase, which is having only the solvent. Okay. Now, how this law, which is important, which is taken as Raoult's law. Raoult's law statement is for a ideal solution. As long as this equation is valid for a system, for a solvent solute system, as long as this equation is valid, we say that Raoult's law is valid. Now, you see, whenever we are talking about this, when we are talking about this pressure, we are talking about the pressure in terms of, whenever we are talking about pressure, we have to understand that the vapor pressure we are talking about, we are taking that vapor pressure to behave as an ideal gas. Okay, that is the approximation we have made. So, even better method would be to consider this equation instead of this for considering a solution which is supposed to be ideal. So, I said in this slide that if the Raoult's law is valid, then this equation should be valid. The partial pressure of the component B in a solution will be equal to the mole fraction of that particular constituent into the partial pressure of the constituent in the pure state, or vapor pressure of the constituent in the pure state. Okay. This is one way of stating Raoult's law for an ideal solution. To when we say the ideal solution, it is ideal solution. That means this equation is valid. But a more appropriate term would be this, because here we have used the approximation that this P is actually the vapor pressure which we are taking is behaving as an ideal gas. But if I take this equation, I do not need that approximation. I just say the chemical potential of that component which is present in excess is equal to the chemical potential of that component in the pure state plus RTLN, the mole fraction of that particular component in the solution. Okay? All of you are with me?
Yes, ma'am.
Okay. So now let us summarize what the Raoult's law states. What we have so far discussed is, at equilibrium, the chemical potential of the vapors form of the solvent A, whichever we are saying this is as a solvent because it is in excess, is equal to the chemical potential of the species which is in the liquid state, okay, or the condensed state. That is the first approximation we made. And we have said this equality will be maintained even if we are adding a small amount of solute, which is also a liquid, B into the system. Because the chemical potential of A in the vapor state depends on the partial vapor pressure of the PA. Okay, that's what we had just now discussed. Whatever I discussed, this is summarized here. So it follows the chemical potential of A, this is mu A, can be related to the partial pressure of the same component, that is solvent Pa. And what does the Raoult's law state? Raoult's law and Henry's law, both of them are again experimentally done. What do you say, that it is observation. Based on the observation, they have tried to make a law. So what Raoult's did, he did experiments with a various number of mixtures, and all these mixtures were one was solvent, one was solute, but all these solvent and solute systems had structures similar, like benzene and methyl benzene, that means benzene and toluene. They are structurally similar. So when he was doing experiments with mixtures having one considered as a solvent and the other considered as a solute, and when he did various experiments, he found the ratio of the mole fraction, partial mole vapor pressure, the ratio of the partial vapor pressure of a component to its vapor pressure at the pure state is equal to the mole fraction of that component in the mixture, in the solution. That was an observation. So observation became a law. And how long is it valid? That means what he's observed for a large number of structurally similar compounds, one considered as a solvent and the other considered as a solute. If you take those sort of solution mixtures, and if you look into the thing, the chemical the partial pressure of the component A to the ratio of the vapor pressure of that particular component in the pure state is equal to the mole fraction of A in the solution. Okay, which can be rewritten as the partial pressure of A, that means component A in the mixture, is nothing but the mole fraction into of that component in the solution into the vapor pressure of that component in the pure state. Okay, are you all clear with what does this mean? This is the partial pressure of the liquid, which is in excess, which is A. The partial pressure of that liquid should be equal to the mole fraction of that liquid into the partial pressure vapor pressure of that liquid in the pure state. Now what about the other component, the component B? Will the component B also have the similar expression? What Raoult's law showed, that not only the component A, that is which is in large excess, but also the component B, which is in minor amount, will also have the same equation valid. That means the partial pressure of B will be equal to the mole fraction of B into the vapor pressure of B in the pure state. Okay, this was his observation, which has become a law. Now
Excuse me, ma'am.
yes.
Ma'am, in one of the previous slides, just the previous before this one, I think, there was P naught in the denominator. What does that P naught signify?
Where? This one.
Relative pressure. PA is equal to, yes, ma'am.
I always write this as a reminder that whenever I'm taking this P, whatever P I'm taking in this equation, okay, chemical potential or the Gibbs equation, this P is always to be remembered that you have a P naught here.
So, ma'am, is that the standard pressure, that is 1 bar?
1 bar, which
Okay.
we do not write. But when you are doing numericals, if you do not take this as 1 bar, if this is not given in 1 bar, then you have to convert that in bar.
Yes, ma'am. Understood.
Okay. Usually we do not write this, but you have to remember that it is always there below. It's just to remind you. In books you will not find, but in lecture notes, when we are talking about, we know that you make mistakes, so we are going to be always time and again reminding you that there is a P naught below. Okay.
Yes, ma'am.
That is 1 bar pressure. Okay. So I hope you have understood this. Now, before we go into the non-ideality or in the solution, I want to remind you what we had done in the mixture of ideal gases. In the ideal gases also we had said, if the total pressure is something, there are two type of gases mixed in the cylinder, then the total pressure is, according to Dalton's law, summation of the partial pressure of the two gases which are present. Okay. And we had said that if I take the pressure for one of the components, when I'm varying with the mole fraction on this side, moles of a species in this side, then, and monitoring the pressure, then for A I will get a partial pressure, B I will get a partial pressure, right? And what is that going to be? That partial pressure is going to be mole fraction into the total pressure, mole fraction into the total pressure. So this is what I was talking in the last class when the class ended. So we had said that if this is the ideal situation, then the pressures are supposed to be like this, and the total vapor pressure should be the summation of the total pressure should be summation of the two partial pressures, which is obtained from the two gases enclosed in the cylinder. But what happens when you have non-ideality, which we have found out what is the measure of the non-ideality? What happens? Because of the interaction of the particles, there is the partial pressures deviate. Okay, this causes a deviation in the partial pressure from the simple mole fraction ratios. So it is no longer exactly the partial pressure of PA is not exactly mole fraction of A into P. P is the total pressure this side, and similarly the partial pressure of B is not exactly B, a mole fraction of B into the total pressure, and this is the deviated line and this is the deviated line. So you can make out the deviation, non-ideal behavior, whenever you have this deviation, and for such deviations, we call them as a non-ideal system, and that exists only when there is interaction between particles that causes the partial pressures to deviate from its simple mole fraction relation. So this relation is not valid. Okay, so deviation starts whenever we have these partial pressure equations, they are no longer valid. If there is no longer valid, means there is some sort of interaction because of which we are not able to maintain the equation which is supposed to be. So similar equation I have generated for uh, the liquid system, where I said if the vapors are behaving like an ideal gas, then I can write the partial vapor pressure of that component A is equal to the mole fraction of that component A into the vapor pressure of that component in a pure state. So this is what we have said. So if I have a deviation, this will be a deviation in this, or the equation, chemical potential equation, which we have generated. Okay. So let us see what is the ideal solution. How do you define an ideal solution? I know that you all know this more or less some bit. If you have a binary mixture which are two liquids which are structurally similar, and one I call is solvent, which is in excess, and the one which is in smaller amount, I call that as solute. Okay. If the solution, ideal solution which we have got is obeying the Raoult's law throughout the composition range of pure A and pure B, such that the total vapor pressure can be expressed as the Dalton's pressure law. That means the total pressure becomes equal to um, the vapor pressure of the pure state A plus the vapor pressure of the pure state B. Okay. If the binary mixture which we are talking about, we are only be sticking to binary now. One is liquid solvent and other is the solute. Both are liquid. If the Raoult's law is valid throughout the composition of the pure A and pure B, such that the total vapor pressure becomes equal to the addition of the vapor pressures of the pure state, where you can write the partial vapor pressure of A is nothing but the mole fraction of A component into the vapor pressure in the pure state of A. Similarly, you can write the partial pressure of B, partial vapor pressure of B is equal to the mole fraction of B in the solution into the vapor pressure of B in the pure form. And from this, we have said this can be derived as the chemical potential. So as long as this chemical potential or this relation is valid for all compositions of pure A to pure B, then we say that the solution is ideal. Let us look at this. Let us look at this diagram. This side is mole fraction of A and this side is pressure. Both the sides I can take pressure. Now, when I move from this side to this side, I'm moving from this side to this side. What I'm monitoring only the partial vapor pressure of A. As I increase the amount of A, since it's a binary system, the B should decrease till I go to a position where at this point no B should be there. Okay. So if I plot the pressure now, the pressure versus the mole fraction, then this line indicates that at XA, that mole fraction equal to 1, that means only A is present, then I should hit the axis for the pure vapor of that component. Similarly, if I take from this side, I say initially the B was this side, I say XB, the arrow should be this side. Arrow will be increasing from 0 to 1 here. So this side, if I have the axis, then I can say the the vapor pressure of the B is initially equal to 0, but gradually as you increase the mole fraction of B, the mole fraction of A keeps decreasing till a point where only B is there. And that time the partial pressure should be equal to the partial pressure of the pure state. Okay. Now, if I look at these lines, if this line is a straight line, that means the partial pressure of A equal to the mole fraction of A into the vapor, the partial pressure, the vapor pressure of the component A. If this line is continuous, if you see, if I'm plotting pressure versus the A, then what is the slope of this curve? What is the slope of this curve? Y equal to mx plus c. This is x-axis mole fraction. This is the pressure. Then what is the slope of this plot? The slope of this plot is the vapor pressure of that component in the pure state, right? All of you agree?
Yes, ma'am.
Okay. So similarly, if I want to look at this line, this is this line, this will be also, the slope will be corresponding to the we are changing the mole fraction from this side to this side. So for this line, the slope will be again the vapor pressure of component B in the pure state. So the vapor pressure in the pure state comes as the slope for this line, which is almost a straight line. As long as you have a straight line for pressure versus composition plot, and the total pressures can be equated to the the vapor pressure of A plus the vapor pressure of B in the pure form, then we say that the Raoult's law is valid. As long as the lines are almost straight. Okay. And if you see, this Raoult's law is more or less valid for the excess liquid. Whichever liquid is in excess, for that, the Raoult's law more or less is a good approximation. For the solvent. Okay, if the solution is dilute. So the condition which we have put in here, that the Raoult's law is valid more so for in a binary mixture, more so for the system which is in excess, that means in the solute, if the solution is very dilute. That means the component B is very small. Okay. So you see the total pressure PT and the two partial pressures PA and PB of a binary systems are proportional to the mole fractions of the compositions. Okay. That is what we had just now. I was explaining. This is the partial pressure of B. This is the partial pressure of A, and this is the total pressure. Okay. So this is an ideal example to show that the Raoult's law is valid. We have a perfect straight line for the partial vapor pressure of A, and a perfect straight line for for the solute, which is another liquid B. And if I add the vapor pressures in the pure state, then I should, for each of the component, then I should get the total pressure. This is an ideal example. For if you want to go on for a real example, let us talk about the benzene toluene thing. Benzene toluene system are structurally very similar. Okay. So if you want to see the slope, what is the slope of the pressure of benzene versus the composition of benzene? That will be equal to the vapor pressure of that of the pure A or pure benzene. And for this, what will be the slope giving rise to? The composition is varied with respect to the composition of toluene with the partial pressure of vapor pressure of toluene. This slope will be nothing but the partial pressure of component B in the pure state. So this slope is going to be the partial pressure of the toluene in the pure state, and the slope for this curve will be the partial pressure of benzene in the pure state when the experiment is performed at a given temperature and pressure. So the variation of partial pressure of each of the components and their mole fractions results in a straight line. And if it is almost a straight line, then we say this Raoult's law is valid. And if the Raoult's law is valid, then this equation should be also holding good, which we have already taken this equation, which is the chemical potential of benzene plus chemical potential of the benzene in the pure state plus RT-ln, the partial vapor pressure of benzene divided by the vapor pressure of pure benzene. Right? Which can be further boiling down to the chemical potential of the benzene in the solution is equal to the chemical potential of benzene in the pure state plus RT-ln, the mole fraction of benzene in the composition in the solution. Right? All of you are with me? All of you are with me?
Yes, ma'am.
So what we can say when we are talking about benzene and toluene system, they are more or less going to show us a ideal behavior, because within the limits they are the the line between the partial vapor pressures of each of the components and their mole fraction is almost a straight line. So that resembles a ideal solution behavior, right? So how do we molecularly justify? How do we justify the uh, Raoult's law? Now, you see, Raoult's law, what does Raoult's law state? Raoult's law states that you have this equation which needs to be valid, right? The partial pressure, partial vapor pressure of component A should be equal to the mole fraction of the component A in the solution into the uh, vapor pressure of that component in the pure state. So what does this mean? How do I get this? When I look into a solution, I have a large excess of the solvent molecules. So these are the solvent molecules which you see, the big ones. They are all in the surface, which we are looking into. And there are some solute molecules which are the smaller ones. Now, if I want to look into the evaporation process, the rate of evaporation, let me write down as VA. Rate of evaporation will depend on what? The amount of gas which is there on the surface, or the amount of liquid which is there on the surface, right? So indirectly the amount, the mole fraction of that particular component on the surface is what is going to be determining the rate of the vaporization process. So I can write the rate of vaporization is directly proportional to the amount which is present, amount of that molecules present, or the mole fraction of that molecule present on the surface. Okay. Now look at the condensation. What happens in the condensation? Rate of condensation will depend on what? How much vapor pressure is there? The concentration of a component in the vapor is going to decide how much condensation is going to take place. So the rate of condensation of that component A in the solution will be equal to will be proportional to the vapor pressure of that particular species in the solution, because vapor pressure means you're talking about the amount of concentration of the species present in the vapor state, right? And this is not usually equal. this is not usually equal. The rate of condensation is higher than the rate of evaporation. That means there is some interaction which is holding the molecule to not escape. Means vaporization means it is going to escape. So there is some something which is blocking the removal of the particle from the surface. So that is the reason the rate of evaporation will be much slower than the rate of condensation, because condensation means already vapor is there, there is no restriction, they will condense. But when you are talking about evaporation, if there are certain molecules which is interacting with the solvent molecules, then they will hinder the escape of that particular solvent particle, right? But at equilibrium, suppose the situation is going on and we reach the equilibrium. At the equilibrium, what will happen? The rate of evaporation should become equal to the rate of vaporization, a condensation. The vaporization rate of vaporization should be equal to the rate of condensation, right? Now you substitute the value of, if you equate these two, equate K into mole fraction of A equal to K prime, it's another rate constant, velocity constant, into the partial pressure of A. Now equate these two, what do you get? You can find out the value of partial pressure of A equal to the ratio of K by K prime. What was that? It was the rate ratio of the two processes which are occurring, right? You can rewrite this, equate these two and find out PA. PA will be what? The K is the velocity constant for vaporization by the velocity constant of the condensation, right? And if they are equated, then what you have? You have the mole fraction of A in that equation. Are you people with me if when I'm showing this?
Yes, ma'am.
So what is happening? That only at equilibrium we can have the rate of evaporation equal to the rate of condensation, and that is the hypothetical situation we have considered. So what we have considered, from equating these two equations, we tried to find out what will be the partial pressure of partial vapor pressure of A when the process of making solution is going on. So what we have, it is going to be the partial pressure of A equal to K by K prime. These are the two rate constant, one for evaporation and one for condensation. Right? Now in this equation, if you consider PA, that is partial vapor pressure of A, is nothing but the K by K prime ratio into, these are some constant, into the mole fraction of A. Suppose you reach a condition where the mole fraction is equal to of A is equal to 1. What does that mean? Mole fraction becoming equal to 1 means addition of all the moles should be equal to 1. Now here what you have, that means the partial pressure which you are talking about is actually nothing but can be equated to the vapor pressure of A at the pure state. This equation, if I put this as 1, if this I say is 1, then what can I write from this? Hurry up. This can be represented as the X mole fraction. So the partial pressure of A becomes equal to the mole fraction of A divided by multiplied by the partial pressure of A in the pure state. This equation is going to be valid and the chemical potential is going to be valid. When will it be valid? When it is approaching ideality and obeying Raoult's law. So the small solute particle, what does it do? The amount of vapor which is generated is hindered of the solvent molecules. But the condensation is not going to be dependent on the solute which you are having. Whatever is going up will be condensing down. So the rate of uh, evaporation, the rate of condensation will be higher than the rate of evaporation. Right?
Yes, ma'am.
Okay. Now I'll take this slide and take a break after that. Now you see, this is a diagram which is showing carbon disulfide and acetone. Okay. Initially, the graphs, all the graphs, if you see, even the previous one, initially all are almost straight to begin with, and deviation sets in. As you know, as you increase the pressure, the deviation starts occurring. Okay. Where ideality is valid only under low concentration for ideal solution. So low concentration means it is indirectly related to the pressure also. So if you can substitute this value P star here, this is becoming P star. So this expression becomes the Raoult's law equation, and that is how you justify.
Excuse me,
Right?
ma'am. Ma'am, I didn't understand how it satisfies or justifies the Raoult's law.
Raoult's law will be justified if you are having this equation valid. What we are
Yes,
right now talking is how to justify that this can be obtained molecular through molecular basis or molecular understanding. How do we get the Raoult's law equation? This is what we were talking about. Understood?
yes, ma'am.
No. How many of you have not understood? I am talking about a solution. Solution will have evaporation taking place. And we are talking about molecules which are there on the surface. The evaporation will take place. If there is interaction between the molecules, then the evaporation will be affected, right? If there are intermolecular forces which is holding the solvent molecule back, then the amount which is going to be vaporized will be less, right? That means how many how much amount of free solvent molecules are there on the surface, that will decide what will be the rate of evaporation, right? That, and moles are going to be proportional to the mole fraction. So this is actually what is rate of evaporation is proportional to the mole fraction of A. When you have some small amount of solute added to the system. But what happens to the condensation process? Condensation means whatever is there in the vapor will come down. There is nothing to hold it back. So the rate of evaporation will not be equal to the rate of condensation if you have certain molecules which is holding the solvent molecule back. And since it is holding back, that means evaporation will be less. Then the amount which is already there in the vapor, that will completely come down in the liquid form after condensation. Is it okay? And how much of that, how the rate of condensation will depend on how much amount of vapor is present. That is going to condense, right? So if I have two equations, one I am talking about evaporation, another I am talking about condensation, and I reach a position where I say that I have reached the equilibrium. If I have reached the equilibrium, then these two rates should be equal. And if these two rates are equal, then I have a process of relating the partial pressure of A, partial vapor pressure of A, with that of the partial, the mole fraction of A. That this is the equation we get, where this is the rate constant in the evaporation process, and this is the rate constant of the condensation process. I get a ratio of the two rate constants. Now, if I say the mole fraction is 1, if I say the mole fraction is 1 under the limit, what does that mean? When will the mole fraction be 1? I put the mole fraction to be 1, then the P star, this becomes P star, right? Because that is the vapor pressure at the of the pure component, right? So I replace P by P star, or I can define this when k x equal to a, xa equal to 1, I can say this expression, this value becomes equal to P star. That should correspond to P star, right? From the equation. And if I now substitute the expression of P star in this equation which I have obtained in the equilibrium condition, then I get what is the expression which is which Raoult's law establishes, right?